The next concept is recombination of spectrum colors. Okay, till now we know that what is spectrum and how it is obtained. Now, what happens when we recombine the spectrum? Okay, now upon recombining the spectrum, what exactly is the resultant color? Now, this experiment was conducted by Isaac Newton. Isaac Newton not only conducted the how to obtain the spectrum using the prism, he also conducted the recombination of spectrum colors. So, what did he observe? Let us see. Now, before going to this particular the phenomenon, you know that let us take a single prism. When a light is passing through the prism, or when a white light is passed through a prism, we have seen that it undergoes dispersion, means splitting up of the white light into its constituent 7 colors. Those 7 colors are nothing but band or spectrum. That is violet, indigo, blue, green, yellow, orange and red. You can see here. Now, in this recombination, so what this Isaac Newton did, he took a prism ABC, is the first prism. Now, very close to this prism, he took one more identical prism. He took one more identical prism of the same prism, but he laterally inverted. He laterally inverted that prism in the opposite direction. He kept close. Okay, and then he wanted to observe whether these spectrum colors will undergo recombination. So, after keeping this identical prism laterally inverted in the opposite direction, where you can see the lateral surface AC and one more lateral surface A dash B dash, very close, opposite to each other. Now, you should know that in the prism ABC, A is the principal angle of the prism. In the prism A dash, B dash and C dash, A dash is the principal angle of the prism. Both are opposite here. Like that, he arranged this particular setup. Next, what he did, he took a white light which is passed through a pinhole of a sheet of paper, so that a narrow beam of white light is incident on the face AB of the first prism ABC. Naturally, within the prism, when the light passes from rarer to denser, we know that it undergoes refraction, which means dispersion itself will happen. So this white light got split up into its constituent 7 colors undergoing refraction. That is, here I have indicated only 2 rays, that is the lowest and the highest. Means the lowest wavelength is violet and the highest wavelength is red. Between that you will get 5 more colors, that is indigo, blue, green, yellow and orange. So this spectrum got refracted at the face AB, and again it got incident on the opposite face AC of the prism ABC, where it underwent the dispersion. Now please be very careful. If there was no prism, second prism ABC, the band of spectrum would have been like, it would have been dispersed. It would have been diverged or dispersed, right? That's why it is called as dispersion. Now, since the other prism is laterally inverted, that is kept in the opposite direction, very close to the first prism, whatever the spectrum, the band of 7 colors that would come out of this face AC, those band, that is all those 7 colors from violet to red, it would travel parallelly, in parallel lines, you can see here. They traveled parallel and got incident on the face A dash B dash of the second identical prism. Now what happened? Now what Newton could observe, since it got incident on the lateral surface A dash B dash, within the prism, that is within the second prism, again these 2 rays should go refraction. But that refraction was opposite to that of the refraction that happened in the first prism ABC. Why? Because you can see the angular dispersion. This is the angular dispersion, you can see here, I have marked this angle. With the same angular dispersion that was happening in the second prism, where here the rays got diverged, here the parallel rays, that is from violet to red, which were incident on the face of the second prism A dash B dash, they were converging after refraction within the prism. they were converging on the face A dash C dash. So that itself was the indication for the Newton that whatever the dispersion that was happening, all those 7 colors were coming very close and they were converging on the face A dash C dash. So outside it, that is when the light passes from denser to rarer, what happens again? Refraction should happen, but that refraction was nothing but a single color, a fine beam of light. A fine beam, a single beam of light. It was white light. As it was that white light, the same white light had been incident on the face AB. The same white light the Newton could see after the refraction through the face A dash C dash, which means he confirmed that the angular dispersion on the prism 1 was equal to the angular dispersion on the other prism, the identical prism. And also all these 7 colors, they got converged and came out as white light. So which means to say that Isaac Newton confirmed that just like sunlight, here we have white light also, which upon dispersion splits up into its constituent colors, as well as they recombine and they can be got back, or through the recombination we can get back the same white light on the screen. So this was the experiment done by the Isaac Newton. So it is recombination of spectrum colors, where all the 7 colors of the spectrum, they just recombine after passing through the 2 identical prism, where one of the prisms is laterally inverted, kept in opposite direction, whose one of the lateral face of the lateral surface is kept close or opposite to that of the other lateral surface, face of the first prism. So this experiment was proved and it was conducted by Sir Isaac Newton. One of the best example or the natural phenomena that we can see in the rainy season when the shower begins, to illustrate about the dispersion is occurrence of rainbow. Right? What exactly is a rainbow? You know that naturally you will get the band of the spectrum of 7 colors, that is violet, indigo, blue, green, yellow, orange and red. So during the rainy season, okay, and in the presence of sunlight, if the shower takes place, obviously you will get the rainbow. Now the primary condition or the what you are observing in nature that some might not be aware of, but you should always be aware that the rainbow will happen if you are observing in the opposite direction to that of in which direction the sun is actually, right? So you are observing the rainbow, that is violet, indigo, blue, green, yellow, orange and red, and these rainbows occur like circular colored arcs in the sky, right? And you should observe opposite to that direction in which the sun is there. Means if the sun is towards this direction, means you are getting the rainbow in that direction. So that is the occurrence of this rainbow. Now, why this rainbow is actually in a form of the circular colored arcs? Okay, circular arcs. Why this happens? This also happens because of the dispersion phenomenon. Now let us explain in detail. You can see here. Now see, this is the earth, and this eye, what I have written is the observer. Now he is looking up. Okay. Now see in which direction the observer is looking, and see the direction of the sun. The direction of the sun is opposite to that direction where the observer is looking. Now you can see these in the nature, okay, in the atmosphere, this the rain showers, or when it rains, you can see in the atmosphere that rainwater is distributed in the form of rain droplets. Okay, raindrops. There are large number of raindrops. Okay. Now each raindrop will act as a prism. It acts as a very small prism. Okay, that circular rain droplet itself will act as a small prism in nature. Now what happens when the sun rays are parallel and when it is coming and when it is going through these raindrops, okay, when the sun rays are coming parallel and falling on these rain droplets, you can see within the rain droplet, this sunlight will undergo refraction. You can see here, it will undergo first refraction where there is bend of light, and within this rain droplet, there is one more phenomenon. Along with the refraction, there is also one more phenomenon, optical phenomenon, that is total internal reflection. Means it is again reflected back. You can see here, this is the refracted ray and it falls on this point of the rain droplet. Again it gets reflected. After reflection, again the ray has to fall on the eye of the observer, right? It again gets refracted. So when it is incident, it undergoes refraction, total internal reflection and back to refraction. Similarly, one more parallel ray, you can see one more ray of light, you can see here, it is falling on the other droplet. Now within the droplet, it underwent refraction, then total internal reflection, again refraction. You can see both the rays are getting converged here. Now the observer is capable, or he is observing all those 7 colors in the form of the arcs like this. Now this is reason. You can see here, it is coming like this. It is undergoing refraction. See, the rays of the sun is coming like this. It is undergoing refraction. It is undergoing total internal reflection, and it is back. So that's why you are observing in the form of circular arc. When you see from the earth, you are observing like this, all the 7 colors. So this is one of the natural phenomena to illustrate dispersion, that is occurrence of rainbow. Okay, this is how the rainbow will happen. Okay. Now let us move to the next concept, that is atmospheric refraction. Okay, you know there are various layers of the atmosphere above the earth. Okay, it can go up to certain level of the atmosphere exists for certain kilometers, right? So what do you mean by atmospheric refraction? It is the phenomenon of bending of light. It is a phenomenon of bending of light when that light passes through the Earth's atmosphere. Okay, usually the sun is situated above the atmosphere in space. Very huge distance. We measure in light years, right? So from that sun, when the sun rays, after passing through the space, that is the vacuum, okay, and again those sun rays, when it reaches the Earth's atmosphere, so there it undergoes refraction. Okay, now to illustrate that, okay, I have taken a simple diagram. You can see here. Now you can see this is the Earth. Okay, and here there is a observer. Here there is an observer. Now, how this observer will be actually see any object which is at very far distance above the earth, means how the refraction will happen. Okay, now you can see I have taken for my convenience many layers of atmosphere. Okay, above the earth the atmosphere exists, and these atmosphere can be split up into many layers. So for the example sake, I have taken 1, 2, 3, 4, 5, 6 layers. Okay, now before the sunrise, you can see here now here is the sun. Now a ray of light is from the sun, actually it is passing. Okay, now before entering into the Earth's atmosphere, means at this level, the first layer, before entering into the first layer, this sun ray there is traveling in the vacuum. Okay, means there is no kind of atmosphere or air or something like that. Okay, at that it is fully a space. When it is traveling through a space, now that is considered as the rarer medium now. Why? Because here the optical density is lesser the optical density. Therefore, its refractive index is less. So usually in refraction, remember, the rarer medium should have lesser refractive index. The denser medium should have more refractive index. That's why when the sunlight travels from the sun and when it reaches the space or the vacuum, there because of the lesser optical density is less, therefore refractive index is less. So that's why it becomes rarer medium. Now in the same ray of light, when it comes and when it strikes the first layer of the atmosphere, this first layer of the atmosphere means what? This N1 is always, this first layer of atmosphere is having the refractive index N1, and this N1 is greater than this N. Right, that's why this N1 is the denser medium and this N is the rarer medium. That vacuum is the rarer medium. So it undergoes refraction. You can see here from first layer to second layer there is bend in the path of light. Now when it reaches second layer, refractive index of the second layer is greater than the refractive index of the first layer. Then this first layer will become rarer medium and second layer will become denser medium. Again it starts bending towards the normal. You can see here. Okay. Now what happens? Consider from second to third layer. When it moves from second to third layer, refractive index of the third layer is greater than the refractive index of the second layer. So again it is bending. Okay. Like this, when it moves from one layer to another layer, the previous layer becomes the rarer medium and the next layer becomes the denser medium. So thereby the optical density, there is variation in the optical density also, and the refraction process will take place. That's why you can see here there is the gradual bending of the light that is going on as and when the sun rays reaches the Earth's atmosphere and travel through the atmosphere due to the variation in the optical density and variation in the refractive index. So the light ray will travel from through the successive layers, where the preceding layer becomes the rarer medium and the succeeding layer becomes the denser medium, so that there is successive bend. Okay. At last, finally, when the observer is looking, okay, where exactly is looking, he will get the ray of light. You can see. Okay. So this is how the atmospheric refraction will takes place. Let us see the examples for the atmospheric refraction. Now, you can see here, the stars appear higher than they actually are. Right? Now, you can see here, students, this is the position of the star, actual position of the star, and this is the apparent position of the star, which means the star which is seen apparently from the ground or from the surface of the earth appears to be at higher position. Actually, star is situated here. Due to this atmospheric refraction, through the various layers of the atmosphere, the refraction, the stars appear to be at a very higher distance. Appear to be, it is apparent, not actual. Actually, the star is at this position. See, H1 is the actual position of the star from the earth. Now, H2 is the apparent position. Now, which is greater? Now, this apparent position is greater than this actual position. Now, why? Very simple. Now, see here, this is the actual position of the star. Now, the light from the star will travel first in the vacuum, okay, that is rarer medium, and when it enters to the Earth's atmosphere, various layers become the denser medium, where the optical density keeps on increasing, okay, and the refractive index also keeps on increasing. So, it undergoes multiple refractions, right, from layer 1 to layer 2 to layer 3, so on. After undergoing multiple refraction, the refracted ray keeps on bending towards the normal, and at last, as seen by the observer, it will reach. Okay, it will reach vertically. Now you just extended the ray using dotted lines vertically upwards, straight. Okay. Now, if you are extending that, you will find that the position of the star, as seen, okay, where the position of the star is at a higher position as compared to the same star which is actually at a lesser height. So this is also one of the phenomenon that happens in the nature, okay, that is stars appear higher than they actually are. So there is the reason for this being is the atmospheric refractions. Next example for the atmospheric refraction is advanced sunrise and delayed sunset. Advanced sunrise and delayed sunset. Now how this happens, let us see. Okay. Now let us go for advanced sunrise. Means the sun appear to be rising in advance. How that happens? That is seen apparently. Okay. Now see here. Now this is actually the earth. Okay. The shaded lines whatever on the center part is the earth. Now the dotted line surrounding the earth is the atmosphere of the earth. The space gap is there, right? Or this gap is there between the earth and this one more circle with the dotted line represents the atmosphere. Now you can see on one of the point on the circumference of this earth, I am drawing a line like a tangent. It passes. Okay, that is called as horizon. Okay, you can see a line which is horizon. Now that horizon line is where actually the observer is. Okay. Now the observer is exactly at the horizon, the level of the horizon on the surface of the earth where he is observing the sunrise. Now you can see here the observer is in the direction of west. He is in the west direction, and you know that the sunrise happens to be in east direction. Both are opposite. Now see here, actually the sun is at the position S is the sun. Now this is horizon. Now you know that actual position of the sun itself, the atmospheric refraction will happen. How? Now see here, sun is very very far away. Still the sun rays has to reach this atmosphere of the earth. Okay, but sun is here. So outside you have the vacuum. So the sun rays travel in the vacuum. Okay, where that vacuum is supposed to be the rarer medium. Once it enters the earth's atmosphere, it undergoes multiple refractions with the various layers of the atmosphere. Okay, so see here, it is undergoing the various refractions, and thereby the light is seen, or the sun is seen by the observer. But this observer who is looking at exactly or near the horizon, the observer near the horizon is not seeing the sun at exactly at this point, and he is seeing the sun well in advance at this position. How? Now you just produce the line backwards. The refracted ray ultimately when it reaches the observer, just produce the line backwards. So it goes as a straight line backwards, and there you can see the apparently seen sun to be above the horizon. So the sun is actually at this position, and 2 minutes before itself, the observer from the west direction, who is sitting near the horizon in the west direction, he is able to see the sun at this position towards the east. So which means to say that the observer will feel that the sun is, or the phenomenon that is happening here means the observer is seeing the apparent rise of the sun 2 minutes before. Before means what? Advanced sunrise. So this is where the observer is seeing the sun S1 at S1 position. Actually the sun is at S position. The delay is 2 minutes before. See here, actual sunrise happens to be at 6:70 a.m. Take an example. The sun is rising at 6:70 a.m. Now apparently seen before advanced sunrise means here it is seen at 6:15 a.m. means 2 minutes before itself we are able to see the sunrise. This phenomenon is also a very good example for atmospheric refraction. Now opposite to that is the delayed sunset. Now the same here, the earth and the encircling circle with the dotted lines is the atmosphere, the various levels of atmosphere. Now you can see the horizon. Now the observer is towards the east, and the sun will set in the west, towards the west. Okay. Now you can see here, it is a delayed sunset. Okay. Now actual sunset is happening at 6:15 p.m. It should happen, but the delayed is seen at 6:17. Means the observer is seeing this sunset at the position S2 at what time? 6:17 p.m. Actually the sun has set. Okay. Actually the sun has set at exactly 6:15 p.m. You can see the sun has gone below the horizon. Actually the sun has gone below the horizon. And from that actual position itself, you should draw the refracted rays. So the sun is very far. So the rays from the sun, when it reaches the Earth's atmosphere, at the first layer itself, it undergoes multiple refractions, and the refracted ray finally enters the observer. But the observer is not seeing the sun, actual setting of the sun below the horizon. He is only seeing the atmospheric refraction, that effect, what had happened, and he is seeing the sun at this position, say S2. Due to the atmospheric refraction, you just produce the ray backwards so that it follows a straight line, and here is the position. So at the apparent position, that is S2, at exactly 6:17 p.m., 2 minutes delay. 2 minutes delay means the sun actually has set at 6:15 p.m. The observer is seeing the sun, the setting sun, to be at apparently to be at 6:17 p.m. So how many minutes delay it is? 2 minutes delay, or 2 minutes later. You use the word. Okay. The observer sees the apparent position of the sun or the delayed sunset 2 minutes later. Here the observer will see the advanced sunrise 2 minutes before. So these two natural phenomena that are happening merely due to the result of atmospheric refraction. Let us move to the next phenomenon, that is scattering of light. Okay. Now for the scattering of light phenomenon, two famous personalities have contributed for this scattering of light. First person is Rayleigh and Tyndall. Okay, and you know, you have already learned in 9th, that is Tyndall effect. Okay. Now what is scattering of light? It is the process of bouncing of electromagnetic radiation by atoms or molecules of a medium through which they are traveling. Okay, so whenever a ray of light is traveling in a particular medium, it gets scattered by the atoms and molecules of that particular medium. That is called as scattering of light. Okay, now you can just see in this example or in this diagram. Now incident light of a particular wavelength lambda. The wavelength is measured, or it is represented by lambda. Okay, and when an incident light of particular lambda enters a particular medium, now what happens? That medium is filled with atoms and molecules. Every atom and every molecule, for that matter, every molecule is a small particle, right? That small particle is called as scatterer. Means that molecule is responsible for this incident light to scatter in different direction. That's why it is called as scatterer, which is represented by small x. Here x represents scatterer. See here, that center you have this scatterer. Now all these are scattered light, means this is the direction in which the incident light is traveling, and these are the directions in which the scattered light is traveling. And the reason for that to happen is the scatterer, that is every molecule or every small particle. Okay, that depends on size also. Every particle of that particular medium is responsible to scatter this particular electromagnetic radiation or incident light with a certain wavelength in different directions. Now, this was this scattering of light phenomenon was observed by Rayleigh. So, this Rayleigh, what he concluded or what he said in his theory, suppose if this scatterer, that is small x, is less than the wavelength of light. This scatterer, the size of the scatterer, if it is less than the wavelength of light, then the scattering of light would happen, means it was valid. The scattering process would have happened only when the size of the scatterer is less than the wavelength of light. Otherwise, if the size of the scatterer or if the size of the particle is greater than the wavelength of the light, that is lambda, x is greater than lambda, this scattering process was not valid in that particular medium. Now, whatever the Rayleigh's conclusions was there, it was proved experimentally by Tyndall. So, Tyndall proved experimentally what were the conclusions that were obtained from Mr. Rayleigh with his own experiments. Okay, so let us see further what he did. Now, let us go for the next, that is Tyndall effect. Okay. Now I told you that whatever the conclusions that was given by the Rayleigh, Tyndall conducted some practical experiments where he could observe the scattering of light phenomenon. Okay. So he defined the scattering of light as it is a phenomenon of scattering of light by colloidal particles. So Tyndall effect is the process of phenomenon in which the light is scattered by the colloidal particles of that particular medium. Okay, we use the word colloidal particles. Now, what are the examples for the Tyndall effect that we can see here? The sunlight entering a smoke-filled room. Okay. Now, whenever a room is filled with smoke, a small fine beam of sunlight, when it is made to enter, so within the path of that sunlight, we are able to observe whatever the particles of smoke is clearly visible when that light is passing through the room which is filled with smoke. Okay, so that is first one. The second is sunlight passing through a dense canopy of forest. Now assume that there is a dense canopy of forest. We have entered a forest. Okay. Now at certain areas or at certain distances you can see the sunlight being entering into the dense canopy and it is falling on the surface. Okay. Now how that sunlight, whenever you can see that sunlight, if you are tracing that, you can see the fine particles that are there. Okay. So sunlight passing through the dense canopy of forest, tiny water droplets, because forest is filled with mist. Okay. Now in that mist, it contains tiny water droplets. Now those tiny water droplets, they scatter the light because those tiny water droplets acts as scatterer. Okay. So they act as scatterer and they scatter the light. So in that only we can see the many particles. Okay. That on the way. Okay, the sunlight passing through the dense canopy of forest, the tiny water droplets that are present in the mist, they scatter the light. So there are many examples that you can give for the Tyndall effect. Now, the observation that we are intended is very important here, these 3 points. Now see here, you know that in the spectrum of Vibgaya, okay, that is violet, indigo, blue, green, yellow, orange and red. In this spectrum of visible spectrum, this blue comes first and red comes last. Okay. Now that blue light is having lesser wavelength. Now, whichever light is having the lesser wavelength, for that light to be scattered, you require the particle size should be smaller. Means the scatterer, the size of the scatterers should be smaller, or size of the particle should be smaller to scatter the light having the smaller wavelength. Remember. Okay, blue light is having the lesser wavelength. So when that particular light, if that particular light has to be scattered, then you have to require the particles or the scatterer to be of smaller in size. Similarly, red comes later, right? So that red is having higher wavelength. The wavelength of the red is very high. So in order to scatter this particular wavelength of light, that is red light, the scatterer or the particles size should be larger. Okay, the size of the scatterer is of a larger size. So very important. So blue light with the lesser wavelength requires the scatterer's size to be small. Then the red light having the greater wavelength or maximum wavelength, the size of the scatterer should be large. Okay. Now, what happens in a medium? Just assume a particular medium in which you have all the particles or all those scatterers to be of very, very large size. Okay. If the size of all the particles is very large, X means scatterers. So if the size of the particles or the scatterer, they are very, very large, what happens? You will not find small particles and you will not find a medium size, nothing like that. All the particles are very large. At that condition, all the wavelengths are scattered, means from violet to red. This whole spectrum comprising, that is the white light comprises of all these 7 colors light of different wavelengths. All these are scattered equally. Okay, all the wavelengths are scattered almost equally, and scattered light appears white. This is the reason why the scattered light appears white. Why? Because in the medium where all these scatterers or the particles are of relatively very, very large size, then in that case the entire wavelength, that is wavelength of all those colors, are scattered almost equally, so that the resultant scattered light appears white. Okay, so this is Tyndall effect. Let us move on to the experimental process of explaining the Tyndall effect. Okay, experiment for observing the scattering of light in colloidal solutions. Now, for this apparatus, for this experiment, let me explain this. Here we have S to be the source of light, that is white light. Okay. Next you have L1, that is the convex lens. The first convex lens, that's why L1. Now you have a transparent glass tank. Okay, a transparent tank which contains, this transparent tank contains 1 liter of clean water mixed with 100 grams of sodium thiosulfate. 1 liter of water, and to which you are adding 100 grams of sodium thiosulfate. Again, to this mixture you are again adding 1 cubic centimeter of concentrated sulfuric acid. I repeat, to this transparent tank we are adding, that is G, represented by G, we are adding 1 liter of clean water and 100 grams of sodium thiosulfate and 1 cubic centimeter of concentrated H2SO4. Then opposite to that you have a cardboard. C is cardboard which is having a narrow hole. To the next you are having one more convex lens L2. Finally you have the screen Y. Okay. Now what happens? Let us see here. Now this glass tank which is transparent and contains the three mixture, that is the three elements mainly added, that is clean water, then you have 100 grams of sodium thiosulfate, then 1 cubic centimeter of concentrated H2SO4. When they mix, the sulfur particles will come out. Okay, and these sulfur particles, they vary in size. Few sulfur particles may be small, few sulfur particles may be medium, and few sulfur particles may be large, relatively large in size. Okay. Now let us see here. Now this source of light, yes, is a white light, and when it is incident on the convex lens, okay, the convex lens is capable of sending those rays parallel. Okay, and these parallel rays will travel through this transparent tank which consists of these three elements. Okay. Now when this white light will travel through this transparent glass tank, what happens is, now this white light is made up of all 7 colors of different wavelengths light. Now the first light or the first color to be scattered, because you will observe scattering here, the scattering process should start here exactly. Now the sulfur particles will quickly be activated, and in this the tiny sulfur particles or the sulfur particles which are very very minute, it is capable of scattering the wavelength of that particular color which is less. Now in Vibgyor, as I have told you, this blue color mainly it is scattered first, which means this is fourth side of the tank. Okay, now see here, this side is fourth side of the tank. This side is fourth side. All remaining 3 sides are there, right? On all those remaining 3 sides, this blue color which is having the lesser wavelength is scattered. Means it is scattered within this glass tank itself. Okay, why? Because the wavelength of the blue color is very very less, and so it requires a smaller colloidal particles of sulfur to be acting as the scatterers. So they scatter this blue light on all the 3 walls of this particular glass tank. Okay, and it is not sent out. All the the sulfur particles, which are very very tiny particles, they are capable of scattering the blue color having the lesser wavelength on all 3 sides of the container. Now you have one more container, fourth side to be there, and which is facing this cardboard having the narrow hole. Now what happens? After this blue light you will get red light in the Vibgyor, right? In the Vibgyor, after blue light you will get red light whose wavelength is very more high, right? So that red color is coming with a mixture of orange and bright crimson red. Now to the side, that is the fourth side which is facing this particular cardboard having this narrow hole, you can see here the rays which are transmitted by the larger sulfur particles, okay, or the sulfur particles or the scatterers which are very large, they are capable of not scattering, they are capable of transmitting the wavelength which are very high, whose wavelength is more in this spectrum. Obviously the red is having the higher wavelength, so the color which is having the higher wavelength is transmitted. The color which is having the lesser wavelength, that is blue color, is scattered in that container itself. So the color which is having the higher wavelength is further transmitted and it is passing through this narrow hole on the cardboard and it is falling on the convex lens. Thereby the convex lens is converging on the screen. You are getting, or you are able to see the orange red color first and then bright crimson red color next. So this indicates that there was no blue light which is obtained here. Why? Because the blue light which was the lesser in wavelength, it got scattered by the tiny sulfur particles, and those sulfur particles which were quite large, they could easily transmit the colors which were the color which was having the higher wavelength, that is the red color. So that's why the red color got transmitted further. Okay, so this experiment indicates that the scattering of light phenomenon takes place in the colloidal solutions by the colloids or by the particles. Okay, means of relatively of larger size as well as smaller size. So smaller size colloidal particles could scatter the color which was having the lesser wavelength, that is blue color. The large size sulfur particles, means a colloid, they could transmit the color which was having the greater wavelength. So this experiment illustrates the scattering of light or the Tyndall effect that we could observe in the colloidal solutions. Another example to illustrate the scattering of light is the sun looks reddish at the time of the sunrise and sunset. This we all have observed. When the sky is clear, when there is no cloud, we can see the rising and the setting sun to be of reddish in color. Now, let us see why that happens. Now you can see here, this is the Earth's surface, okay, and here is the observer. You can see the observer here, and above the Earth's surface, the space. This is Earth's atmosphere. Okay, this is the Earth's atmosphere. Usually, the sun, the rising sun, and the setting sun, or the setting sun appears to be happening near the horizon. So that's why I have written the sun, that is the rising or the setting sun near the horizon, and the sun is above the observer's head. Yes, on top of the observer head. That's why I have written overhead. Let us see first here why the sun look reddish at the time of sunrise and sunset. You can see here the sun which is in the verge of rising or setting near the horizon. The sunlight, when it enters the atmosphere, the distance being very large, and the atmospheric layer or the larger portion of the atmosphere is there, so it undergoes scattering here. Why? Because the Earth's atmosphere consists of many colloidal particles, many particles of small, large size, right? So the tiny particles were able to scatter the color of lesser wavelength. So which was the color having the lesser wavelength? That is blue. So you can see here the blue color got scattered more as it travelled through the larger portion of the Earth's atmosphere. Okay. So that's why the blue scattered more, and only the color which was transmitted very easily as it could be seen by the observer was the red color. So the sun appears to be reddish. Okay. Now you can see the same sun on the overhead of the observer. Here the rays of the sun falling normally, it is falling normally on the observer side, okay, and why it appears, the sun at the overhead appears white, it is not red. Why? Because there is less scattering here. The blue scattering is very, very less. Why? Because the ray is travelling at lesser portion of the Earth's atmosphere. Here, larger portion of the Earth's atmosphere was there, so scattering was more. Here you can see here only this much portion of the scattering is happening, means the scattering is very less, or the blue scattering is very less. So that's why, since the scattering itself is going very less, what happened? We could see only the white color of the sun to be transmitted overall. Why? Because the scattering was less as the Earth's atmosphere through which the sunlight is traveling, it was very, very less. So it traveled through the very lesser or few portions of this Earth's atmosphere, so that the scattering process was very, very less. So that's why we could observe the white color of the sun when it is at the overhead, whereas the same sun when it is to be rising or setting near the horizon, it appears to be reddish in nature. So this completes the second chapter.